Yeah, thank you for the introduction and the invitation. It's so exciting to be back in Waterloo, which was my home for like 4.5 years, and it's just been really great to be back. So today I'm going to be talking about something which is a little different for me, and that is the connection between first-order logic and graph theory and computational complexity. So the idea whenever we care about first-order logic is that you only care about graph properties that can be expressed using certain rules. And so I'm just going to start by telling you what those rules are. And this is going to be the first-order logic. So I'm allowed to quantify over vertices. I can say things like there exists a vertex v, and for all vertices u. I can use logical connectives, so and, or, implies, whatever you want in that regard. And I can ask if two vertices are adjacent or equal. And that's it. This is the complete, this is what I'm going to give as the complete definition of the first-order logic of graphs. So let's go through an example. It's always really difficult to look at actual sentences written in first-order logic, so let's not try to look at this just yet. But say that the property that I'm interested in is whether G has a universal vertex, one vertex that's adjacent to all of the others. So the way I can write that using just those rules is I can say there exists a vertex v, so that for every vertex u, and then I'd iterate through all of the vertices and actually look at them, either u is adjacent to v or u is equal to v. Okay, so you'd say that the property of having a universal vertex is expressible in first-order logic. And the sentence itself, I'll usually write by the symbol phi. So phi is a sentence. And whenever I say it's a sentence, all that means is that for any graph, it's either true or false. That's what it means to be a sentence. All right, and so if phi is true for a graph G, we say G models phi, and that's written this way, using this symbol. Okay, and so now we're doing model theory. All right, and I actually took a model theory class here with Rahim Musa, so this is still where I got started in all of that. So we have some intuition that some graph properties are more complicated than other graph properties. I think it's kind of intuitive that having a triangle is a more simple graph property than having an odd cycle, and that's more simple than having a Hamiltonian cycle, a cycle that uses all of the vertices in the graph. And using logic, we can actually formalize the fact that these properties are getting more and more complicated. So the first property you can state using first-order logic. I can say there exists vertices A, B, and C, and A is adjacent to B, and B is adjacent to C, and whichever one I missed. Yeah, so the point is you have to actually write out all of those things. I can't say in first-order logic these things are pairwise adjacent. That's not the sort of thing I can do. I have to actually say for each pair that they're adjacent. But you can still do this because there's only 3 vertices. And if you want to say that you contain an odd cycle, well, one natural way of doing that is saying that the graph is not bipartite. So one way I can write this is I can say there do not exist sets of vertices x and y. So now this is not a first-order sentence because I'm not just talking about single vertices, I'm talking about sets of vertices. And anything that you can write by talking about sets of vertices, this is called the first kind of monadic second-order logic for graphs. And if you can write it using quantification over sets of edges, that's the second kind of monadic second-order logic for graphs. So something like Hamiltonian cycle, you can write by talking about, by saying that there exists a set of edges f, so that every vertex is incident to exactly 2 other vertices via edges in f. And also, anytime I look at the partition of the vertex set, there's at least one edge crossing that partition. So it is possible to phrase this property that a graph contains a Hamiltonian cycle by using these previous rules plus quantification over sets of edges. Okay, so in the first kind, we're only allowed to talk about individual vertices. Here we're allowed to talk about sets of vertices, and here we're also allowed to talk about sets of edges. And this is kind of the best possible, so it's true that you can't, there's no monadic second-order sentence of the first kind which expresses the property that a graph contains a Hamiltonian cycle. So really there's no way of avoiding the edge set quantification. Even if you tried to come up with some other thing that was really equivalent to having a Hamiltonian cycle but was worded differently, it's just impossible to do it. So you can show things like that. There's really no way of wording this property using just quantification over sets of vertices. And likewise, there's no first order sentence which expresses the property that G contains an odd cycle. And I want to give a proof for this, which is really fun. This is like a stereotypical logical proof, and I think it's really different from a lot of the things that we're used to. So I think it's a nice example to give. Yeah, so I'm going to show that there's no first order sentence. That is, no sentence that uses just quantification over individual vertices, logical connectives, and talking about vertices being adjacent or equal, that expresses the property G contains an odd cycle. All right, and it's going to be a proof by contradiction. So I'm going to suppose that such a sentence does exist. And it's not going to be obvious why I'm doing this right away, but just follow me through the proof for a minute. So what I'm going to notice is, well, we already know how to express that there's a cycle of length 3. Likewise, I can express that there's a cycle of length 5. So for each fixed odd length, I can express in first order logic that there's a cycle of that particular length. So for each k, there does exist a first order sentence. Phi k expressing G does contain a cycle of length 2k plus 1. And I'm going to actually express G does not contain a cycle of length 2k plus 1. And now let's consider a finite set of these sentences. So a finite set of the sentences saying, I have an odd cycle, but I don't have an odd cycle of length 3. I don't have an odd cycle of length 5. And if I take a sufficiently large cycle, then every sentence in S is true for that. Yeah, because this does have an odd cycle, but it doesn't have any short odd cycle. So every sentence in S is true for a sufficiently long cycle. And by compactness, which is a theorem in first order logic, so I'm not going to tell you what it says, but compactness says that as long as every finite subset of this holds for some graph, then actually there exists a graph so that all of these sentences hold. So by compactness, there exists a graph. It doesn't have to be finite, okay, but there exists a graph. So that every sentence in that set holds for G. Okay, but now this is a graph that has an odd cycle, but yet it doesn't. Yeah, so it has an odd cycle, but not one of any finite length, and this isn't possible. Yeah, so actually if you think about it, every cycle is finite. There's no way of defining like an infinite cycle, and you could even like try to do that and imagine trying to do that, but there's really no way to do it. Okay, and I think that that proof is really fun. I know it might seem a little weird, and I want to say that this really is like an honest proof. If you don't believe in infinite graphs or something, there are other proofs that work. But this is my favorite because it is using this classic theorem about first-order logic, the compactness theorem. And I also mention this because this is a very stereotypical example of the sort of thing that holds for first-order logic, but doesn't hold for other logics once you allow like edge set quantification and stuff. So there's no version of compactness for these languages. All right, so in general, as you go from left to right, these languages are having more and more expressive power. There's more graph properties that you can state if you allow for quantification over sets of vertices or sets of edges. And conversely, the problems are getting harder and harder to solve. So it's harder to test if a graph contains a Hamiltonian cycle than it is to test if a graph contains a triangle. And I want to talk about the trade-off between that sort of expressive power and computational tractability, and also between how complicated the graphs are that we're trying to solve these problems on. Yeah, so just to give an example of the sort of problem that we're going to solve, so a Hamiltonian cycle, this is an NP-hard problem. So there exists problems that you can state in this language that are NP-hard. And likewise, that's true for this first kind of monadic second-order logic. So we talked about how you could say that a graph is not bipartite. And likewise, you can say that a graph is three-colorable using just those rules. You can say there exists sets of vertices x, y, and z. And then you can talk about, that giving you a three-coloring. But first-order logic is unique because each first-order problem can be solved in polynomial time. And that's what I want to talk about now. So given a problem that I can state in first-order logic, given, say, a sentence in first-order logic, I want to determine whether or not that sentence holds for a particular graph. Okay, so let's consider this example. This is the first-order sentence that says, my graph contains a triangle. There exist three vertices that are pairwise adjacent. So how can we test this? Well, the naive way is to go through and iterate through all of the vertices and consider that vertex as A, iterate through all of the vertices and consider that vertex as B, and the same for C. And after you check all triples of vertices, you can tell whether or not there's a triangle. Yeah, so this is the naive algorithm for first-order logic, and this works in general. Yeah, so I'm only ever going to run into there exists a vertex or for all vertices. And either way, I just iterate through everything and check it. So in general, the naive algorithm runs in time order n, which is the number of vertices, to the length of the sentence. Or really, you can do a bit better because the running time is more about the quantifier depth. But I don't want to get into that. All right, so we can check for a triangle in time n cubed. And if you really want to optimize this, you can do better. There's some really pretty proofs that show you that you can use matrix multiplication to test if a graph contains a triangle. So you can beat the exponent by a bit. But there's a complexity assumption that tells you that you can never, this exponent has to grow with phi. Okay, so this is the complexity assumption, that the exponent has to grow with a sentence length. So to be more precise, in fact, it's true that under the exponential time hypothesis, you cannot remove phi from the exponent. There has to be some dependence. So in particular, so intuitively, I'm saying you cannot remove phi from the exponents. And what that means is that you can't do something like for each fixed first order sentence phi, you can't have an algorithm that runs in time n to the power million. Right, so yeah, for any like constant you can put in the exponent, you can't have an algorithm that runs in this time. So just, yeah, intuitively phi has to be somewhere in the exponent. All right, so what I'm going to be talking about for the rest of the day is for which graph classes can you remove phi from the exponents. So just to give an example of that, there's a theorem of Dvorak, Crowell, and Thomas that says that you can check for triangles in planar graphs in linear time. You can actually beat this by a lot. And their theorem works for general first order sentences. So for planar graphs, graphs that I can draw on the surface without crossings, you can check every first order property in linear time. And I think, by the way, this is really surprising and is a really fun fact to think about. Like, if you've worked on planar graphs before, you maybe know that there's a linear time algorithm to see if a graph embeds in the plane. And that already is really not easy to see. And then it's not even easy to see that once you have the embedding, you can check for a triangle in linear time. So even just for the special case of triangles, this is a really nice theorem. But actually, the proof doesn't use the embedding at all. It's like a different, completely different type of thing. And in fact, it's a logical thing. It's like a quantifier elimination kind of thing. So I'm not going to get into that. But this is really, really pretty. And this is the kind of thing we're trying to do, but we want a dichotomy theorem. We want to know exactly which classes I can do this sort of thing for. All right, so the question is going to be for which classes of graphs are first order properties efficiently checkable? And efficient here means that there exists some constant, possibly depending on the class, so that you can check a property phi on a graph in the class in time into the D. So whenever I put something in the subscript on big O notation, it means that the constant factors depend on that. Yeah, and please feel free to stop me if there are any questions throughout all this.
So what is the subscript phi indicate, like the constant factor?
Yeah, exactly. Yeah. Yeah, so to be a bit more precise, what this means is that there's some function depending on phi, and then the time is n to the d. Yeah, so this is the running time. And by the way, I framed it this way so that it looks like a more general dichotomy conjecture. Yeah, for which graph classes can you solve first order properties efficiently? But actually, we think that as soon as you get like even 1 million here, actually you should get 2. So really we think that as soon as you can check first order properties, even like mildly efficiently, as long as your class is closed under taking induced subgraphs, you can actually check it in time quadratic for a fixed property. But this is like, I mean, we're a ways away from this. Okay. Yeah, are there any other questions? All right, I put up the definition of efficient again. Yeah, there exists a D, so you can check with an n-vertex graph in the class. Models a first order sentence phi in this kind of time. And really, you want something kind of explicit about what the time is. Yeah, from now on, I'm going to assume that the class is closed under vertex deletion. So if I've got any graph in the class and any vertex of that graph, I can delete it, and what I get is still in the class. You need this kind of thing in order to make the problem more about the structure of graphs in the class rather than the size of graphs in the class. And this is kind of the mildest assumption that's reasonable to make. Okay, so the folklore conjecture, it was, I think, stated by a lot of people at about the same time, is that a class of graphs admits an efficient algorithm for checking first-order properties, if and only if it has good model-theoretic properties, in the sense of Shayla, who is, I think, definitely the most famous model theorist. So now I'm going to tell you more about what these good model-theoretic properties are. If anyone does model theory, it's being NIP, but that's kind of not the name I like, so we're going to use a different one. And there's a lot that's known about the conjecture already. In particular, it's true if the class is sparse, that is, if it has little of n squared, many edges. As soon as there's not that many edges in the graph, it turns out that having good model-theoretic properties is equivalent to forbidding shallow minors, which is one of my favorite things. What that means is that for every integer r, there's some graph that can depend on r that I forbid as an r shallow minor, where an r shallow minor is 1 so that the bags that I'm contracting have radius at most r. Yeah, so I'm not going to go into that if you are not a fan of minors, but I just wanted to say that having good model-theoretic properties, if you're sparse, is the same thing as having like nice structural graph theory properties in some sense. Yes, this is really pretty, and this is why I got into this, and this is how this area relates to my work at Waterloo. I think this is really nice, so I had to mention it, but I'm not actually going to talk about it. Okay, and so there's a lot that's known. Dvorak, Kroll, and Thomas in this algorithm, they found an algorithm in a special case, and they proved hardness in the general case. Adler and Adler found the connection to model theory, which really is not obvious. And Grohe, Kreutzer, and Sieberts found the actual algorithm that works in general. And what my work does is it generalizes this stuff to show that this conjecture is also true if the class is edge stable. And what edge stable means, so this, by the way, is also a property that comes from model theory, but I'm not going to say why, because it's much simpler to just state it explicitly. So edge stable means that I don't have this kind of graph induced between the two sides. So now let me give you an actual proper definition. Right, so the half graph, I'll draw a picture of H4, is going to have 4 vertices on either side. And each vertex is adjacent to its partner on the other side and everything below it. So this is called a half graph, and a class is edge stable. If there exists an integer k so that no graph in the class contains sets of vertices A and B, so that if I look at the edges joining A and B, I get exactly the half graph of size k. So what I mean by this is that I don't care what happens on either of the two sides, but between these aren't the edges that I get. And the way this comes up from the model theory perspective is that half graphs are viewed as linear orders. If you care about first order logic, half graphs are exactly the things that are linear orders. So they're like linear order free. And by the way, this is a generalization because every sparse class, in particular, it forbids a complete bipartite graph, and half graphs have big complete bipartite graphs if I look between the top half here, and the bottom half here is a complete bipartite graph.
Can you elaborate what you mean by improved hardness as in matching the algorithm?
Yeah, okay, good question. Yeah, so they showed that if you, either you get the efficient algorithm, or finding an efficient algorithm on this class is as hard as finding an efficient algorithm on the class of all graphs. Yeah, so yeah, this is the,
So it's a dichotomy.
yeah, exactly.
It's not that it's always easy, it's that there's a characterization
Yeah.
in there. Okay.
Yeah, exactly. Yeah, and the hardness direction is, let's see which direction. So you can show that if you have good model theoretic properties, then you have an efficient algorithm. The other direction is saying if there's not an efficient algorithm, well, whatever, the other direction uses the assumption that, for instance, you could assume ETH, but really they're assuming something weaker.
Kind of fixed parameter tractability.
Yeah, that's exactly, yeah, yeah. No, exactly, yeah. So the hardness assumption is usually stated as FPT does not equal AW star, and AW star is like less well known than the usual FPT hardness stuff, but this exactly means that you can't have an efficient algorithm on the class of all graphs. Yeah, and you can state like having a 3-vertex clique in first order logic, and this is, yeah, the connection. Any other questions? All right. Yeah, so I worked on this with a group of people at Warsaw, and we also ended up combining the paper with another group that had simultaneously solved the problem in Germany. So this is the hardest part of the talk. This is with Gajarski, Malman, Ullman, Pilipchuk, Przebeszewski, Siebert, Sokołowski, and Turunchik. Yeah, so there's a few different steps to this in order to get the whole dichotomy conjecture under the assumption that you forbid a half graph. One of the parts is that we showed an equivalent characterization of classes with good model theoretic properties in terms of a certain player having a winning strategy in a combinatorial game. And then Dreyer, Malman, and Sieberts found the actual algorithm, but they were still missing a piece. Kind of everyone knew that the algorithm should work, but you needed to solve some conjecture in order to get the algorithm does work. And then we solved that conjecture with Dreyer, Eleftheriadis, Malman, Pilipchuk, and Turunchik. And this, by the way, is Michał Pilipchuk. There's two brothers. Yeah, and we also proved the hardness side. All right, so now I want to tell you about the good model theoretic properties, because I've been very hand-wavy about this. All right. So what does it mean for a class to have good model theoretic properties? It means that no formula has the independence properties. This is called not the independence property, and that's SNP. But we've just been calling it dependent because it's not independent. So I'll say F is dependent. If you cannot use a first order formula, I'll tell you an example in a second. This is like a sentence with free variables. There's some things that aren't quantified over. So in this case, it will have 2 free variables for vertices to define the class of all graphs. So let me give you an example to show what this means. I think that does it the best. So I can look at, for instance, the formula that says these vertices x and y are either adjacent or there exists a vertex w which is adjacent to both of them. Yeah, so I've only used the same rules that I've told you about, asking whether two vertices are adjacent and quantification over vertices. I see some people squinting a little bit. Let me say what this says. This says either x is adjacent to y or there exists a vertex w which is adjacent to both x and y.
How does the F come up in that definition?
How does that, yeah, so when applied to graphs in F is, I didn't really finish. And I'll say what that means in a second. Yeah, this is not really a careful definition. I hope that'll be clear after I do the example. So the type of formula I mean is this kind of thing. I use the rules that I've already talked about to give some statement. This formula is true for two vertices if those vertices are joined by an edge or by a path of length 2. And now if I start with a graph, G, and I'll always be considering only graphs in my class, I can apply this formula to get a new graph. In this case, the formula is going to give me the power graph. So what I'll do is I'll put a vertex for every vertex of G. So the vertex sets are going to be the same. And then I join two vertices if this formula is true for those vertices in this graph. Yeah, so I put an edge between two vertices if they're adjacent or if there's a path of length at most 2 joining them. So the adjacent ones would give me these edges, and then, yeah, in the neighborhood, I'm going to add a clique everywhere. So something like this. Yeah, so a class is dependent if for any formula with two free vertex variables, if I apply this formula to all of the graphs in my class to get a new class of graphs, this class still doesn't contain all graphs. In fact, the closure under vertex deletion doesn't contain all graphs. Okay, but this is the idea. It's like you can't use your class to define the class of all graphs.
So is it okay to think of this phi xy thing as playing the analog of reductions for you?
Yeah, absolutely. Yeah, and this is how the hardness is always, yeah, going and everything. Yeah. Yeah, and you can kind of say that two things are logically equivalent, but only if you can undo the formula as well. So that you're often interested as well. Like in order to, this reduction kind of only goes one way. I'm going to mention a couple of things really fast. So on this side, you're also allowed to delete vertices. So that's what I mean by contains. And you're also allowed to color vertices. And then your sentence can say things like, and you can color vertices in any way you want. So I think of it as being like a non-deterministic process. I look at every coloring. And then your formula can also say things like, and the color of a vertex is red. Okay, so those are mainly technical aspects, but I just wanted to mention it so I'm not lying. Yeah, so basically a class is, has good model-theoretic properties if it doesn't define all graphs. And I mentioned that the case of having a forbidden half graph actually comes up naturally here. And so if instead of defining all graphs, you care about defining all half graphs, that's really what we're looking at. So we say that a class is stable, like not just edge stable, but stable, if you cannot use first order formula to define the class of all half graphs. There's also a theorem that says that a class is stable if and only if it's edge stable and dependent. I mean, we don't need to know that, but I'm just saying that this is really, like, the two notions are really connected. And this is kind of the next most natural case that people in model theory study. Yeah, so stable means you can't define all linear orders as well, is another way to think about it. So sometimes people call these classes order-free. All right, and now I want to talk about the key ingredients to the algorithm. And the first key ingredient is something that lets you not have to use this definition at all, because we showed that this definition is equivalent to a certain player having a winning strategy in a combinatorial game. So I want to tell you about that game. All right, so for this game, it's called the radius r flipper game, and is played for a particular radius r. There's two players, flipper and connector. They both have complete information. They can even know each other's strategies and everything. And they take turns. So what the flipper player is going to do is they're going to flip. What does that mean? So you select a set of vertices x, and you replace the graph induced on x by its complement. So if this is my set x, then between vertices and x, I change edges for non-edges, and vice versa. So this is what it means to flip on a set X. And this is another way that this stuff is related to what I was working on at Waterloo with Jim. This is the same basic operation that we have for other things we're interested in. Yeah, so flipping means I select a set of vertices, and within that set, I exchange edges for non-edges. And really, it turns out that these two graphs are logically equivalent. I won't say why, but yeah, they're logically equivalent. And the game goes as follows. So in every round, if there's only one vertex left, then flipper wins in that round. So flipper's trying to get rid of all of the vertices in the graph to make it so that connector has no more moves. And connector is trying to keep the possibilities open. And then connector picks a vertex v, and you restrict to the ball of radius r around v. And flipper performs a flip, and you continue. Yeah, so in every round, if there's no more interesting moves for connector, then flipper wins. Otherwise, connector chooses a vertex, and you restrict to a small ball around that vertex, and then flipper flips. Okay, so let's go through this with an actual example. This is going to be with radius 2. So this is my graph. To begin with, there's more than one vertex. So connector will pick a vertex, this one, and I'll restrict the ball of radius 2 around that vertex. That means that I keep this vertex, I keep its neighbors, and I keep their neighbors. And I get rid of everything else. And then flipper performs a flip. Maybe flipper will select these vertices, and then within that set, exchange edges for non-edges. And now we go to the next round. So there's still more than one vertex. Connector picks a vertex, and you restrict the ball of radius 2. Flipper flips on some sets, and then connector chooses a vertex. Maybe they chose this vertex, but that's wrong, because in the next round, there'll only be one vertex left, and so flipper wins. Okay, so I should have maybe said this before. This is like some analog of a pursuit evasion game where connector is the robber and can run R steps in any round, but then instead of cops, you have this magical flipper person who, yeah, instead of putting a cop on a vertex, they just flip some edges in the graph. And the goal is for the cops to catch the robber in a bounded number of rounds. Okay, so Flipper wins if there exists a bound on the number of rounds, which depends on R, so that for every graph in the class, they can win after at most T rounds. Yeah, so the goal is to catch connector after a bounded number of rounds. Yeah, so it turns out that this is equivalent. It's not at all obvious why this would be equivalent. I mean, you can go here to this graph, the half graph, and you can kind of check, and you can see that connector has a winning strategy. Connector can always run away for a long amount of time. And so this kind of thing is how you can prove one direction. That's the easy direction. The hard direction is showing that if you don't define all half graphs, then Flipper has a winning strategy. Because you go from something that's avoided to the existence of a winning strategy, which is more explicit, more concrete. So that's why this is the hard direction. All right, so I want to talk a little bit more about the final ingredients to the algorithm. And so Dreyer, Malman, and Sieberts, in giving the actual algorithm, they used LP rounding tools. There's like a pruning of the game tree arguments where you say that actually you don't have to consider every way this game could have possibly played out. You can only consider some of the like back and forth moves. And then there's a locality argument, which is another thing that's unique to first order logic. Locality basically says that if two vertices are far enough apart in a graph, then the value of a formula only depends on what happens around x and what happens around y. So like this particular thing that we looked at said, put an edge between x and y if x and y are joined by a path of length at most 2. And locality says every first order formula kind of looks like that. You only care about what's going on locally. And then the final thing is something called neighborhood complexity, which relates to VC dimension and the theory of set systems. And this is something, so what we proved is that if your class is stable, that is if it doesn't define all half graphs, then for any set of n vertices in the graph, the number of different neighborhoods a vertex can have within A is almost linear. So yeah, what this says is that for any graph in my class, then you set A of n vertices in the class, the number of different neighborhoods vertices can have within A is very close to the size of A. I kind of think of this as like an expansion thing. I mean, I know it's not the same. Like this works much better for graphs that are dense. So like if I've got two vertices that have exactly the same neighborhood in A, I can throw away one of them because they act the same way to A. And this says that once I do that, the neighborhood of A doesn't grow too much. I think this is really surprising. And yeah, by the way, the 1.001, of course, is not particular. This is for any like positive epsilon. So this shows up a lot in the theory of set systems. But what's unique here is that we're getting almost a linear bound. So not just polynomial or anything. It really has to like be almost linear for this to work, for the algorithms. And there's a conjecture that says that the same bound holds if the class is dependent. So as long as you have good model-theoretic properties. And I think, yeah, so we are very close to proving this. And the last thing that I want to mention is that there's this wonderful conjecture of Patrice Osona de Mendez that says that actually nothing we've done here is new. You can reduce it all to the sparse case. Yeah, so the conjecture says that every class that's stable is interdefinable in like this kind of sense, with a class that's sparse. And if you could do this in an algorithmic way, you'd actually reduce all of the stable stuff to the sparse case. And this would also be a structure theorem for stable classes. It would tell you exactly what the stable classes are. They're the ones that come from these sparse classes. All right, thank you.
Thanks. Any questions? I can start. So one of the things that I was thinking about with these classes is you're kind of thinking about these classes of graphs and defining them as some sort of other thing. Is there any relation of if I, took I think you called it a modal second order theory, and I defined something with that, does then that tell me something about the properties you were thinking about?
Yeah, you can do all of the analogous sort of stuff with other languages. Actually, if people here have seen tree width or clique width, that's the kind of stuff you get if you can't use monadic second order logic to define all graphs, then this is kind of conjecturally, but it's also kind of known to be true that, yeah, you have bounded tree width or rank width. Yeah, it's possible to formalize all that.
So at the end is the algorithm and LP relaxation and not?
Yeah, there's a step where you do an LP rounding, and yeah, you use lemmas about VC dimension and everything to get the LP rounding.
Is it just one shot, or are you sort of using it as a subcomponent?
Yeah, so I can actually say what this is used for. So it turns out that as long as you have this kind of small complexity thing, you can find a collection of sets of vertices so that each one has bounded radius, like is contained in the small ball around some vertex. And also so that for every vertex, its neighborhood is contained in something in your collection. And no vertex is in too many of the things in the collection. So this kind of approximates the neighborhood of vertices. And it turns out that the LP part is mainly showing that as long as such a thing exists, then you can find it. Yeah, so you can, I think it's one shot.
The number of such components is what? I mean, is that
Like linear.
Okay.
Or almost linear, yeah, like into the 1.001.
That gives me a sense for how the LP is looking for this. Okay, thank you.
Mm-hmm.
So I'm not sure if this is a valid question, but the not good model theoretic property is it NP. So can you certify that lack of good model theoretic property?
Yeah, I would say that, yeah, so if it has a bad model theoretic property, it's because there's some formula that defines all graphs. Yeah, and so like as an algorithmic thing, can you say what this formula is? Yes, I think even not algorithmic, not algorithmically, I can tell you that this formula has a special form. It basically is this formula, the one that I've given, but with higher radius. As for the algorithmic thing, like, can you actually say how large of a radius do you need? I don't know. I'd have to think about it.
No, not algorithmic. Yes, I was asking about NP, so just a certification. So that there's no notion of pi.
I mean, I'm not sure how to formalize this exactly because, like, the thing that defines a 10-vertex graph might be contained within a really, really giant graph. So I'm not sure. I'll have to think about that.
It's been a long time since I did model theory, but you're pointing out that, of course, first order logic has a lot of tools that you don't have beyond that. But I seem to recall that monadic second order has tools too that are more like
Yeah.
for say games and stuff like that, right?
Yeah,
So,
right.
I mean, obviously, I'm not going to get a lot of good complexity results, but like, can I usefully say, well, there's nice stuff, nice graph theoretic stuff I can do in MSO? that I can't do
Yeah,
beyond that?
absolutely. So the main question that people have studied is a little bit different, which is why I didn't go into detail. But the main question people have studied is, okay, this is maybe going to sound funny. So, like, given a class of trees, say, is there an algorithm that tells me which sentences are true for all trees? Yeah, so is there an algorithm that takes in an MSO sentence phi and tells me phi is true for all trees? Like, what are the theorems? Yeah, we obviously would like to have an algorithm that tells me which things are theorems. You do have an algorithm for trees, actually. Yeah, so there's an algorithm that tells you which statements are theorems for trees, as long as they're stated using just quantification over vertices, over vertex sets. And actually, you can go beyond trees. So you can ask for which classes is there an algorithm that tells me their theorems. And this is the main thing that people have studied, and the dividing line is kind of the same, actually. The dividing line is still having good model-theoretic properties in this sense. And yeah, I was trying to think before the talk about actually this problem for other languages, and I'm not sure.